Hello, in this session I shall continue with some examples on vectors. Right, I'll start by talking about independent vectors. Now to understand what independent vectors mean, let me just recap on something that I have explained in the last session. In the last session, I've talked about parallel vectors. Now, for two vectors that are parallel, say a vector A and a vector B, suppose that they point in the same direction, but they have different lengths. So for parallel vectors like that, I can always express one vector as some number, let's say h times another vector A. So if I look at an example, say when this vector B is twice as long as the vector A, then I can say that I can write down B is equal to 2 times A. Now, there is another way to think about this relation. I can also say that this vector B, it depends on A, in the sense that B is equal to twice of A. So in that sense, we can think of this relation as a kind of dependence. Dependence in that, suppose that this vector B must always be some number, some scalar times the vector A, then it depends on A in that sense, in the sense that it must always be some number times the vector A. And when this happens, then B must always be parallel to A. So we think about the idea of depending, one vector depending on another in this sense. So if we take this idea a bit further, let's think about a vector that does not depend on A. Now, since, as we have said, depending means that if one vector is equal to a number times another vector, then it's said to depend on that vector, like B depends on A. Then I can think of a vector where I cannot write it as a scalar times A. And since this only happens when the vectors are parallel, that simply means that I have to think of a vector in a different direction, like a vector C, like that has a different direction from A. So in this case, I can never ever write C as a number times A. Never. Because no matter what number I choose, C is simply not in the direction of A. So if I multiply A by a number, I can only make A longer, but I can't change the direction. So in that sense, C does not depend on A. So if we think about vectors that are independent, there is a useful thing that we can do with vectors that are independent. So let me write this out. If I have a vector let's say A, and another vector B that are in different directions, then we know that they must be independent, in the sense that I can't get this vector B by multiplying A by a certain number. So that's what we understand. Now what can we do with this pair of vectors? Let's look at an example. Now suppose that I make up a vector like this. Say 3 times of A plus 2 times of B. I'm just going to make this a little bit shorter, make it easier to draw. Right, that's B, that's A. Now, let's start by looking at that example. How can I draw such a vector? Right, let's start with 3A. 3A is a vector that is in the same direction as A, but it is 3 times longer. So 1 time, 2 times, 3 times. Right. So 3A would be that. That's 3A. And 2B is a vector that is in the same direction as B but twice as long. So 2B would go from there to there. That would be 2B. So this addition, this 3A plus 2B, the answer is given when we complete this parallelogram. If you think of these two arrows as the sides of a parallelogram and complete the figure like that, then I can get this vector, this resultant vector, by joining the opposite corners to form a new vector. So this vector would be 3A plus 2B. Right, so I've got that, but what does it mean? Well, what it means is that you can imagine making up, say, another vector by changing those two numbers. Suppose that instead of 3, I change it to 1.5, and instead of 2, I change it to 3. Okay, now if I do that, then what I'm doing is that I'm changing the length of 3A to 1.5. So I might have a vector there which goes up roughly by this amount, and 2B changes to 3B would give a vector that is a bit longer. And if I think about adding those two vectors to form the resultant vector of this sum, I need to complete this parallelogram. Alright, and I will end up with a new vector that looks like that. So if you think of it this way, then you'll find that simply by changing the numbers that I use to multiply by A and by B before I add them together, I can make up vectors that have different directions and different lengths. And in fact, I can make up any vector I like by choosing the suitable numbers for A and for B. So what does that really mean? Right, let me clean this away. I can think of it in this way. Starting from A and B again. Now let's think about it in the opposite way. Suppose that I have a certain vector like that. I can actually express it in terms of A and B by finding a number to multiply by A plus a number to multiply by B. Now the reason is that all I need to do is to extend B and extend A. Okay, and from the tip of that arrow, draw a line that is parallel to A, draw a line that is parallel to B to form a parallelogram. Right? And we can see that this vector, alright, something, just any vector that I choose, can be written as the sum of this vector and the sum of that vector. And this vector we know is in the same direction of B, so therefore it will be some number times B. And that vector is in the direction of A, so it can be written as some number times A. So in that sense, if I just pick any vector I like, it can be that one or one in a different direction and a different length, I can always express it in terms of A and B. And from this picture, you can see that there is only one way that we can do it. Because if you imagine actually doing this drawing yourself, if you're given A, B, and you're given this new vector, there is only one way that you can actually draw this parallelogram. Therefore, you have a definite value, a definite length for each of these sides along B and along A, and therefore you will be able to find definite numbers to multiply by the A and by the B. So in this way we can combine A and B like that in order to get any vector we like. So how is this useful? Well, suppose that if I think of this adding of the A, combining of the A and B by multiplying each of A and B by a certain number. Now suppose that I don't know what the numbers are in the beginning. I can represent them by symbols like H and K. So if I multiply A by some unknown number H and B by some unknown number K and add them together, alright, I can think of it as forming a parallelogram like that and giving me a new vector. Now suppose then that the question tells me that this is actually equal to some definite expression like maybe 3A plus 2B. So if in a question we are given that this combination, alright, in which the multiplying numbers are unknown, is actually equal to this 3A plus 2B, then we can actually get the unknown numbers simply by comparing the two sides. So in this case, since on the right side A is multiplied by the number of 3, and on the left side A is multiplied by H, this means that h must actually be equal to 3. And since kb is equal to 2b, it means that k must be equal to 2. So this is one very simple way to use this this idea of forming a vector from the two vectors in different direction. Now, but you might start wondering, what is the point of doing this? I seem to be just making up an example which does not seem very useful. Now, in order to see how to use this, we need to look at some examples. They're actually quite useful. So let's start with this question. We are given this figure. It's a big triangle there with a line across it. So those two lines are parallel. Right. And right, the points here are labeled with these letters A, D, B, C and E. And we are given that the ratio of the lengths AD to DB is 4:1. So the 4 and the 1 here is a ratio. Right. And the question is to prove that AE here is equal to 4 times of EC. So that's EC there. So let's try to work this out. Right, let's define some vectors. Let's start by defining some vectors. So we know that we can express AE in terms of AD and DE, right? Because we have a triangle there. If I think about AD as a vector, then and AE also as a vector, then let me just draw a double arrow there just to show that this means parallel. So we know that AD, the vector AD plus vector DE is equal to the vector AE. Right, let me write that out. the vector A D plus the vector D E is equal to the vector A E. So to make things easier, let me represent these vectors, these two vectors, by a symbol. Right, so let me call this vector A and this vector B. So what we have here is A, the vector A plus the vector little b is equal to A, E. Alright, that looks slightly simpler. Now what about the vector A, B? Now the vector A, B is longer than the vector A, D, and we know that the ratio there is 4:1. So that means that AB is longer than AD by a factor of 5/4. Alright, because the ratio is 4:1. So if we think of AD as having 4 parts, then AB must be 5 parts. So AD, okay, let me write down AD. So AD AB, actually I want to express AB in terms of AD. So AB is actually AD multiplied by a number to make AD longer, and that number would be 5/4. Alright, because that's 5 parts and that's 4 parts. Alright. Next, we'll look at BC. Now we know that BC is parallel to DE. So this means that BC must be some number multiplied by the vector B. So it must be some number. Now we don't know what that number is, we just know that because they're parallel, BC we must be able to write BC as a scalar multiplied by the other vector which is parallel to it. So let that number be k. So it will be k times b. So BC must be some scalar number multiplied by b. Right. Now let me change the AD to A. So this is actually 5/4 times little a. So why are we doing this? Right, it's because we want to express AC in terms of A and B, in terms of the vectors A and B, so that hopefully we can somehow prove this relation. So bear with me. Now, if I write down the relation between the vectors along the bigger triangle, we know that the vector AB plus the vector BC must be equal to AC. So the vector AB plus the vector BC must be equal to AC. Now, using these relations that we have obtained, let me write the whole lot in terms of the vectors little a and little b. So we know from here that AB is equal to 5 over 4a, and that BC is equal to a scalar times b, in which we let the scalar be k. So this is k times b. Now, so finally, AC would be equal to, now we want to somehow relate this to the previous equation there. In other words, we want to relate AC to AE. Now, if you compare AC and AE, you see that they're actually in the same direction. And this means that AC must be some number, some scalar multiplied by AE. So let that number be, say, H. So I can say that AC must be equal to, say, some number H multiplied by AE. And we know from the earlier equation that AE is equal to actually little a plus little b. So if I substitute this into there, I get H times A plus B. So that's the equation that we are after. If you look at these two equations, what you see here is you see that A and B are combined together in the same way that I described just now, where I talked about, if you remember, two vectors in different directions, and we multiply one vector by a number, the other vector by another number, and we add those up to form a new vector. And that's exactly what's happening here. We are adding this vector to that vector, and this one is the AB, that vector is the AC. So adding these two together gives this vector. Now in this case, I'm also adding A plus B and then multiplying by the H. So what's happening is that I'm adding little a to little b to get AE. Okay, and then this is multiplied by the H to give you AC. Right, but how can we use this result? The way to use this result is to say that we can compare the two sides. Right, we have 5 over a here on the left side. Now on the right side, we have h times a. So that means that h must be equal to 5 over 4. So that gives us immediately the answer for h. And if we know that h is actually 5 over 4, we will be able to put it in there to find AC. So this result is already telling us that h must be equal to 5 over 4, and that AC, which is there, must be equal to 5 over 4 times AE. So in other words, AC and AE are in the ratio 5:4, meaning that if this is 4 parts, this must be 1 part, so that we have a total of 5 parts, and AE is 4 parts and AC is 5 parts. So they must be in this ratio. exactly the same ratio as between AD and AB, right? So therefore, from this result, we can now get the answer for this. Prove that AE is equal to 4 times of EC. We want to prove that AE is equal to 4 times of EC. And we have actually got that already, because we have just shown from this result that the ratio of AE to EC is 4:1. So therefore, that simply means that AE is actually 4 times of EC, which is what we set out to prove. So this is how we can make use of the idea of independent vectors to actually calculate answers for questions like this. Now in this case, of course, by choosing to do it purely using vectors, we are taking a very long way, using a very long method to solve something which has a very simple answer. And the answer is that these two triangles are actually similar triangles, right? And we know that in similar triangles, the ratios of the corresponding sides must be equal. So from this simple fact alone, we already know that the ratio of AC to AE must be the same as the ratio of AB to B to AD. And we can actually get the answer to this quite easily using similar triangles instead of having to go through all this vector algebra. But this example of going through it with vectors is useful for us to understand how we can actually use the idea of independent vectors and parallel vectors in order to calculate the lengths of figures like that. And there are many examples in which we do not actually have a simple figure like that with two similar triangles, and in which vector algebra is often the only way for us to get to the answer. Right, so let's move on to the next example then. Right, before I move on to the next example, let me just summarize the previous result again very quickly so that you can see how you should actually write this out if you see the question in an exam. Right. Okay, we are given that the ratio of these two sides is 4:1, and we must prove that AE is equal to 4 EC. So the way to do that, as I've done, is to let this vector, alright, first of all those two are parallel. So I'll let this vector be letter A and that vector there be letter B. Alright? And I then say that the vector AE there is actually A plus B. So we can see that directly on the triangle. Alright. Then we look at the bigger triangle there and say that, right, AB if you look at the vector AB, because the length of AB is 5 over 4 times AD. Let me write this out, because AB over AD is actually 5 over 4 because of that ratio. Therefore, the vector AB must be 5 over 4 times AD, which is the letter A there. Okay, and BC, because it's parallel to little b, therefore it must be little b multiplied by some number, which I let it be k. Alright, I let that number be k. So BC is actually equal to KB. We just let the vector BC be a number times the vector B. Now we have to remember here that we can't just let any vector be a number times any other vector. The vector BC has to be parallel to the vector B. The vector BC has to be parallel to B before we can do that. Alright? So, and the reason why we want to look at AB and BC is because we can add them, add AB and BC to get AC, and then relate AC to A plus B to form our equation. Right, so let me write this down. From this vector triangle, we know that the vector AB plus the vector BC must be equal to the vector AC. Alright, and AB we already know is 5/4 A, and BC we know is K times B, and AC we know is parallel to A plus B, so we must be able to write it as a scalar times A plus B. So if we let that scalar be H, then it's H times A plus B. Now once we have reached here, we can now compare the multiples, the factors for each of the vectors. So for the vector A, alright, on the left side the factor is 5 over 4, and on the right side the factor is H. So 5 over 4 must be equal to H. And likewise for the factor B. For the vector B, the factor on the left side is K, and the factor on the right side is H times B. So this gives us the answer. Alright, it tells us that H is actually equal to 5 over 4. So since H is 5 over 4, K is also 5 over 4. And we can now use this result to answer the question. Right. H, if we remember, refers to this number that we multiply by A plus B. Now A plus B is actually AE, if you recall. This is AE. Okay. So what we are saying is that if I take H, okay, which is 5/4, 5 over 4, right, if I take 5 over 4 and multiply by AE, I must get AC, because that, or rather that is actually AC. So 5/4 of AE is equal to AC. That's AC, that's AE. So this gives us the ratio. Alright, this tells us that the ratio of AC to AE is 5/4. Alright, this ratio of AC to AE is 5:4. And therefore, if I bring this over here, therefore the ratio of AE to EC okay, remember from here AC is 5 parts, AE is 4 parts. So AC is 5 parts and AE is 4 parts. So EC must be 1 part in this ratio. So therefore, the ratio of AE to EC is 4 parts to 1 part. Okay, and we now have the answer. Simply rearrange this and we will get what we set out to prove, that AE is actually equal to 4 times of EC. So that's how we would present our answer to such a question. Okay, so we'll stop here for this session. See you next time.